Okay. Good morning, everyone. Can you all confirm if you can hear me clearly? Okay, so I want to welcome you to another statistical machine learning class. Before I get started today, I want to say this. I have updated the lecture material that I posted. If you go to the canvas, you're actually going to see I've updated this lecture material. So I'm just trying to let you know. Now, let me tell you this. Um, I'm also going to say this. If you send me messages for 2 days and you've not seen my reply, okay, probably your message didn't get to me. So I've already talked to the tech, and because when students visit my office hour yesterday, somebody said he sent me a message and I said I didn't see it. So I've complained to the tech. So when you make sure you resend the message. So my email is working perfectly now. Okay. So let me say this. We're going to be going so tough, okay? And I need you to pay attention. What we're going to be doing from now is going to be highly mathematical, okay? But the moment you ask question, you're going to be fine. Okay, so I want to welcome you to theory of convex functions, okay? In the outline, I'm going to walk you through examples, you know, of convex function from univariate to multivariate. Then I'm going to discuss different types of convex that we have, convex function we have, both the straight and the strong. Then I'm going to talk about the first and second order characterization of convex functions. Then going to give you examples. Okay, so just like what I said, I need you to pay attention. Okay, I want us to have a recap. Why, why do we need convex function? Probably we're doing something, okay, and that requires convex function. And what is that? Maybe we are interested in optimization. If we're interested in optimization, we minimize a function or we maximize a function. The example that I want to showcase today, what if I want to minimize a function? Okay. Or maybe a company is interested in bringing down production cost. Okay. And this particular company, uh, you know, they are not interested in bringing down production costs in just one department. They want to bring down production costs in all departments. Okay, so if you take a look at what I have, just 1 second. If you take a look at what I have a function f of w. Okay, f of w, I want to minimize, and uh, w actually is a member of a set C. Okay, now if I want to minimize, there are so many modules in statistics and in the machine learning world. you know, uh, where our ambition or our intention is to minimize. An example is a least square. Has anybody heard about least square model? Okay, in statistics, we got a least squared. Okay, we may want to minimize, the function. So there are different kind of functions that we may want to minimize. But let me tell you this. If I want to minimize a function, okay, I need to investigate the convexity of that function. Why is the convexity very important? Because all convex functions are very easy to optimize. I'm going to say that again. Why do I need convex functions? Because, when it comes to optimization, okay, it's very easy working with convex functions. Does that make sense? Now, you know our intention, why we need convex functions. So what I want to walk you through now is we need some theory. What are the theories that guide convex function? Okay, that's how we're going to go. But right now, take a look at this. When I talk about a convex set, okay, you know the other time I said f of w is a function and w lies in a set C. Before a function can be a convex, the set has to be convex. I'm going to say that again. A W lies in a set C, okay? And, we have a function of W, a function that is depending on W that we want to optimize, okay? And we expect that function, okay, to be convex. Before the function can be convex, then the set has to be convex. Okay, and right now I'm trying to define what do we mean by a convex set. Okay, now I'm trying to show you a picture of a convex set. Okay, when you see the polygon, we take a look at the circle, you take a look at this. These are convex because they are convex. When you take any 2 points, it's going to fall within any 2 point, and you draw a line segment, it's going to fall within this and that. But when you do that here, it's not going to fall. Okay, and that was what I said a set C is convex if the line between any 2 points stay also in the set. So in the first two picture, it stay in the set. That's why it's a convex. But in the third one, it doesn't stay in the set. That is not a convex. Does that make sense? Now I'm going to move right now. Now let me tell you this. In the definition of convex function, I'm actually going to be using different differentiability classes. We have different differentiability classes that I'm actually going to be called C0, C1, and C2. What is C0? Okay, we take a look at the C0 here. C0 means I have a continuous function. Okay, a function that is continuous. C1 means I have a continuous function with a continuous first derivative. I'm going to say that again. C1 means a continuous function with a continuous first derivative. C2 means a continuous function with a continuous first and second derivative. Does that make sense? Okay, I'm actually going to be using the three classes of differentiable to actually explain the converse function. Now, when you see C0 here, okay, I said a C0 converse, a function is converse if the area above the function is also a converse set. It is required that the area above that is also a converse set. And I said, a C0 function is converse if a function always lies below the chord between the point, which I'm still going to show you. Okay, for C1, don't forget I said C1. C1, it means the function is actually continuous and has first derivative. And that was why I said, when I say first derivative, I said the C1 function is going to be a converse if the function is always above its target place. Now, for the C2, has to be curved everywhere because before, it has to be continuous. The first derivative and the second derivative also need to be continuous. So it is require a quadratic growth, at least a quadratic growth. It has to curve everywhere, not just within a neighborhood of the domain. It has to be curved in the entire domain. And that is exactly what I mean. And what is this condition that we actually going to impose? I needed to take a look at this. That means second derivative. The second derivative of the function has to be greater or equal to 0. Okay? The second derivative has to be greater or equal to 0. Okay, now I'm going to quickly show you some examples. Okay, if you want to investigate convexity, if you are working with a function for optimization and you want to investigate convexity, you can use what I call a second order condition. Now, if you take a look at all of these functions, okay, I can investigate that the second derivative will be greater or equal to 0 for all w in all of these. quadratic, linear, constant, exponential, negative logarithm, negative entropy, and logistic laws. You can also investigate that. So I'm giving you example. These are univariate examples of convex functions. Why do I call it univariate? Because I'm only focusing on one variable at a time. If you look at the quadratic, I'm focusing on variable W. Okay, linear, variable W. In all of this, I'm only focusing on one variable. Does that make sense? Any question? Okay, I'm moving. I want to go into, like I said the other time, I want to use C0, C1, and C2. Don't forget, the C0, the function is continuous. The C1, the function is both, continuous and also have a continuous first derivative. C2, the function is continuous and it's continuous at both first and the second derivative. Now, I want you to see a clear picture, okay, of how a convex is going to look like. Okay, I said a function f is convex if the area above the function is also a convex set. The area above, if you take a look at this particular shape now, okay, if I take 2 points, okay, the 2 points here will lie above the curve. You can see. And this is a curve. We actually want a typical convex function, to mimic that of a quadratic growth. Because with the quadratic growth, the algorithm is not going to get stuck in a local minimum. We want a global minimum, okay? And that is the reason why we require that, okay? But we have an equation. I was talking about chord. Go ahead. Oh, you mean, oh, okay. The point, oh, okay. What I'm going to do is, okay, can you see this, right? Okay, maybe I'm going to be using that. Thank you for that. Okay, now I want to talk about using equation. If I have on this line segment, I have W and V. Do you see? W and V are 2 points in the line. And I try to look at the weighted, the linear combination of W and V. Okay, and I put it in a function. This is a linear combination. That theta is just talking about the transition parameter. Okay, and I put it into a function. That is what we call a convex comb. According to convex law, that should be less than, okay, the weighted average of the functions. This is a weighted average. Please pay attention. This guy here, if you take a look at this guy, that's a weighted average. That's what we call a chord. Okay, we actually expect the function to be below the curve. The chord. That was why you see that function is less or equal to the chord. Okay, so in a situation where this occur, okay, we can actually say that's a convex. But let me tell you this. We got different types of convex that we're going to talk about. But right now, I just wanted to see the diagrammatical representation of a convex function and using equation. Now, the convex chord must be less or equal to the chord, as you can see. And let me also tell you this. Situation, if I'm using the first derivative, if I'm using a Taylor approach, okay, situation where this guy, the first derivative of the function equal to 0, then we can guarantee that any local minimum will translate to global minimum. Don't forget, we don't want local minimum. We want global minimum. Okay, now I'm gonna move right now. I want to talk about the convexity of norms. You've heard about norms. We've done norms in this class. Now, somebody could ask, is norm convex? We can investigate. We can investigate using C0, using C1, using C2, whichever way you want to investigate us. Now, by C0 definition, okay, we can actually show that all norms are convex. How are we going to show this? Don't forget, we have an equation, okay? If this equation is satisfied, we can actually boastfully say, okay, it's convex. Now, let's do the investigation now. Okay, we want to do the, like I said, this is mathematical. Now, you are given a function to be that. Please pay attention. Focus on the board. If you don't understand, ask me question. Now, you are given a function that is a norm of W. I remember in this class, we did what we call the norm, the length, we did the length of the norm. You remember we did all of that. Now, how am I going to investigate whether this is actually convex? Okay. Now, if I want to investigate, okay, if f of W equal to that, I'm actually going to write that in this form, okay, and I'll be able to see whether it's going to be equal to that, it's going to be less or equal to that. And how am I going to do that? Pay attention. How am I going to do that? Okay, I'm actually, you remember, this is coming from the law of equality or inequality. Okay, now instead of me to say from here, if f of W equal to the norm of that, using the law, f of that is going to be equal to the norm of that. Is there anyone who doesn't understand how I relate that to be that, given the function given is a norm of W, all what I'm just going to do is to look into the formula of inequality and rewrite that. Okay, so it's going to be, instead of f of W, okay, instead of me to have f of W, I'm actually going to have theta W plus 1 minus theta, okay, W, okay, which is what you are having. Sorry, we have to use a different point, okay, W and another point, because we're always going to have like two different points to connect a line. Go ahead. Question is really well. Yeah, yeah. So what the function? What if this is what you are giving? Please pay attention. Uh, this is 1 second. You were given this. You can be given any function. Now this function, okay, is a function of W, but we want to take any 2 points, W and V, because for you to in the definition, how many points do we normally consider? You see W and V, right? 2 points to connect a line, right? Now we take W and V, okay, which is what we're doing here, right? Now, if you take W and V, now, if you take a look, this guy now, I'm now going to write it as a norm of this guy, because I'm using this. This implies what I have here now. Does that make sense? It's also going to be a norm. Don't forget, the function of the weighted of the 2 point is less or equal to the sum of the weighted function. That is exactly what we are interpreting. And why I said this is going to be more mathematical, you have to go back to high school now. Please pay attention. We're going to go back to high school. Okay. 1 second. We're going to go back to high school. This is where we are. Okay. We are here, right? If I have the absolute value of the addition, if I have the absolute value of addition of this, I can split them. I can do this and do this. But when I do that, then there's going to be inequality. You remember you did that in high school. So right here now, I'm splitting. The first one, addition of the that actually have norm, then I'm giving each of them, each component norm. But when I give each component norm, okay, please pay attention. When I give each component norm, there will be a less or equal to it created. And that is according to the triangular inequality. Does that make sense? You know, this is less or equal to that according to triangular inequality law. Now, after that, we now want to use absolute homogeneity, okay, where if I have the product, I can split them as well. That's what I'm doing here. I split them. And let me also tell you this. Theta here is a weight. It's a transition parameter. It's going to be a positive. The norm of a positive is a positive. Then that will lead us to this. You can see here, I now have theta. Okay, I have 1 minus theta. They are no longer inside a norm because they are positive numbers. And after that, oh my God, there is something that is showing up. Take a look at this. That guy now is the f of w. That was where we write f of w. This guy will be f of v. Then we've succeeded. Can you see that? So when you have 2 points, okay, each point is going to have its function. So what we've done here, we can now see that f is always below the chord. Whenever we can rewrite the left hand side, okay, less or equal to the right hand side, then we can be rest assured that the f is below the chord. When f is below the chord, it is convex. So, and let me also tell you this. All norms are convex. That is the generalization. All square norms. Okay, I said. Also note, all square norms are convex. All of these are convex. You can investigate them. They are convex because they will satisfy that law of convexity. Does that make sense? Now, I want to move right now. Now, let me tell you this. If I have f of w, if I have 2 different functions, and each of them, they are convex, okay? If I perform a mathematical operation on a function that is convex, can I still preserve that convexity? That's what I want to show you now. Okay, you know, I have f and g. F is a function, g is a function. They are both convex, okay, because they satisfy the law of convexity. So what I want to do now is, let's say for instance, I do this. 1 second, let me see. Okay, if I do that, what am I doing? Fw is a convex, and I multiply by a non-negative value. Alpha is a non-negative value, okay, which means I'm scaling that. Then I'm still going to preserve the new function that will be formed. The new function that will be formed is h of w is also going to be a convex. Does that make sense? So if f of w is a convex, if I scale that with non-negative, I'm still going to have a convex. Now, if 2 functions are convex, okay, and I add them up, okay, if you take a look at this, f of w is a function, g of w is a convex, I add them up, then the new function is also going to be a convex. Okay, we're able to preserve that convexity. If I'm focusing on, maybe I have 2 functions and I'm only focusing maybe on the maximum of the two functions. The maximum of the two functions is still going to be a converse. What of in a situation where I'm doing composition? I remember in middle school, when you have f of s, g of s, you want to find f of g of s or g of f of s. You put a function in another function, okay? But if what you are putting is linear, I have a w, and and I want to plug in a w, where I have a linear combination, that is still going to preserve convexity. And that's exactly what I mean. But let me tell you this. If it is not linear, if you're putting a different function, okay, compositions, and that's why you need to take note of this guy. Please pay attention. I said, but note that composition of converse of f and g is not converse. Even if f is converse, g is converse, the composition is not. Okay, I think I just discussed operations that will enable us to preserve convexity. I'm actually moving. I want to talk about the convexity of a vector machine. Has anybody heard about vector machines in machine learning? Okay, thank you so much. Now, I want you to see something now. We want to apply the properties of convexity, okay, to the vector machine. Now, take it. I said if f and g are convex function, the following preserve convexity. We just talked about the non-negative scaling, the sum, the maximum, the composition with only linear. Every other composition, not convex. Now, let us now put that into consideration now. And let us apply, oh my God, take a look at this. This is an algorithm, or this is a function that we may want to minimize, okay, in vector machines. Okay, and let us investigate, because the only way I can easily optimize this particular function and fully actualize my goal is when it is convex. And because of that, I need to investigate this for convexity. Now, let me tell you this. If you're investigating this for convexity, I want you to look at this part. Okay, let me do this. Look at this part. If you look at their part, all square normal convex, and I multiply by lambda over 2. If lambda over 2 is a non-negative scaling, then that part is convex. You remember? Non-negative scaling is convex. Then let's come to this part. Oh my God, let's come to this part. What do you see here? Mass. What are we talking about? Maximum of two functions is also convex. Therefore, I investigate each part for convexity. They all pass convexity. Then I'm actually going to say the whole function is convex. That's what I mean. Then I'm actually going to move right now. Okay, now you understand that? I'm going to move. Okay, now I've talked about, go ahead. Okay, I should go back to the last slide. No, that is vector machines. The vector machines are one of the, let me just say, algorithm used in machine learning to achieve a goal. But when we get there, okay, we're still gonna discuss vector machines as a topic in this class. But right now, you know what we're dealing with? We're just dealing with a functions to be optimized in vector machine. We're trying to see whether we're investigating the function for convexity. We can investigate whatever function for optimization for convexity. Okay, now I want to move right now. I want to go to C1 definition. Okay, I think I talked about, now let me tell you this, in the C1 definition, I said a function is continuous and its continuous first derivative. If you take a look at this, we can rewrite that, you know, uh, as a, as a Taylor series where I'm expecting f should be always above the target plane. Why do we say above? See, f of v has to be greater or equal to that. Okay, but let me now tell you this. In a situation where this guy, you can see the target plane, you see the blue line, okay, and you see the curve. The curve is above that. You see that line? The curve is above that. And let me tell you this, situation where the first derivative equal to 0, you're only going to expect this to be equal to this. Okay, when this equal, when this guy becomes 0, then you're actually going to say you're going to have, you can guarantee global minimum. Otherwise, we may not be able to guarantee global minimum. I quickly want to move right now. Okay, now when you are using C1, I talk about first derivative, continuous first derivative. If I'm using C2, I want to talk about continuous function with both continuous first and second derivative. Now, because of that, take a look at this. You see that guy having a square, right? That's a second derivative. Without a square, that's a first derivative. The C1, okay, the C1 is first derivative, and that's why you see that very data. That D operator is not squared. But when you take a look at the one, or if you take a look at the C2 now, that is second derivative, and I need you to pay attention. I'm actually going to have a matrix, and that very matrix is actually going to be called Asian matrix in the diagonal. Okay, 1 second. In the diagonal of the matrix, 1 second. Okay, in the diagonal of the matrix, I'm differentiating with respect to the variable 2 times. I've differentiated with respect to W1. I'm going to differentiate with respect to W1. Okay, I do it with respect to W2. I do it with respect to W. So if you take a look at the diagonal, in the off diagonal, when I differentiate with respect to W1, then I will differentiate with respect to W2. So this is what we call Asian matrix. And let me tell you this, the second derivative is the same in statistics as X transpose X. I remember in this class, I walk you through covariance matrix. In the covariance matrix, the diagonal in the covariance matrix are the variances, the off diagonals are the covariances. Okay, now we're actually going to make use of this in determining convexity as well. We use C0, we use C1, we use C2. Now, I want to move. What is going to be the condition that we're going to impose on the C2? The second derivative should be greater or equal to 0 for convexity. Does that make sense? The second derivative should be greater or equal to 0 for convexity. And what we actually mean, greater or equal to 0 means it should be quadratic everywhere. It should be curved everywhere. We don't want a situation whereby in some neighborhood is going to be flat. When it is flat in some neighborhood, okay, the algorithm can get stuck. We don't want the algorithm to get stuck in a local local minimum. We actually want a global minimum, and that is the reason for this. Okay, and of course, when it is greater or equal to 0, we're going to call a positive semi-definite. When it is strictly greater than 0, we're going to call that positive definite. Okay, and of course, we can investigate all of this. Okay. Now, I want us to focus on the least square. We're seeking in least square, we want to solve a minimization problem. You're working on linear regression. You have so many parameters. You want to estimate parameters in linear regression. There's an approach that we call OLS. Has anybody heard about OLS? Ordinary least square approach. The least square approach is a way of estimating regression parameter, by way of minimizing the sum of square error. You want to minimize sum of square error. That's why it's called least square. Now, the least square, the f of w, the f of w is this. It's like a norm. It's a square norm. A least square is a square norm. Okay. Now, when I perform the second derivative will automatically give me S transpose X. And I can investigate that if that is greater or equal to 0, then I'm actually going to say convexity is here. Does that make sense? And why am I targeting convexity? Because it's going to make optimization very easy to do, very easier to do compared to other non-convex functions. So if I want to investigate, please pay attention. I want to investigate that this is going to hold. If I can actually, okay, if you take a look at the function itself here, this is a non-negative scaling. 1/2 is positive, right? And all square norm are convex. F of W itself is a convex. Does that make sense? All square norm is a convex. And when I multiply by non-negative, it's also going to be a non-negative scaling. It's also going to preserve convexity. But I can investigate further. And finally, I'm actually going to get, when you take a look at this guy, okay, S transpose S. And in the S transpose S, I want to introduce 2 points. The 2 points that we always see to U and V. I put U, you can see U there, U transpose, and I put V transpose and V at the other hand. Okay. And if you take a look at the law, mathematical law, you take a look at this guy. Okay. Now, if this guy is the same thing, if I focus on this, the transpose of that, I can rewrite that as SU transpose. And in the end, this is going to end up in a square norm. All square norm are convex. Okay, I quickly want to move because of my time. I want to move. Okay, now these are what I've already talked about. Okay, I've talked about all of this, but I want to move right now. Okay, we have if you are using second derivative, you need to investigate your matrix. Is your matrix positive semi-definite or it is positive definite? If it is positive definite, the second derivative should be strictly greater than 0. If it is semi-positive, then it's going to include 0. Okay. And if I have two different matrices, okay, A minus B, okay, is positive definite. And the way we can do that, we can look at the eigenvalues of A minus B all has to be non-negative. If you get your lambda, okay, they all have to be non-negative. None of them should be negative, okay? And that's exactly what I mean. I'm moving. Okay, I want to tell you this. There are different types of convexity. But the best one that will guarantee global minimum is the strong convexity. Okay, I'm going to differentiate between convexity, strict convexity, and strong convexity. When I talk about, and I can use C0, C1, or C2 to explain that. But right now, I want to use C2 to explain convexity. And I need you to pay attention. When I'm using C2, I'm using second derivative. Okay, now for all convexity, Or in all convexity, when you have the second derivative greater or equal to 0, that function is convex. Convex is different from strict convex. Strict convex is different from strong. If I want to talk to you according to the hierarchy, right? The first one is convexity. Convexity is less than strict convexity. Strict convexity is less than strong. I'm going to tell you why strong is the best. But let's talk about let's use C2 to explain convexity. The moment the second derivative is greater or equal to 0, I have convexity. But you know what? It's going to be strictly convex when it is greater than 0. What do I mean by strictly convex? Oh, okay. I'm going to use this as an example. If f of s, if f of w equal to w, that will give a straight line, right? A straight line is convex, but it is not strictly convex. It is because there's no curve, and it is not strongly convex. Now, for strictly convex, an example of a strictly convex is w raised to power 4. I'm going to show you. When you draw the picture of w raised to power 4, is even though it's curved, it's going to be flat at something near 0. We don't want flatness. We want the curve to be uniform. When the curve is uniform, when the curve is quadratic, everywhere that is strongly convex. An example of a strongly convex is w squared, w raised to power 2. Okay, the curve is everywhere. But w raised to power 4, I'm going to show you the picture. You're going to see. So if I want to differentiate, take a look at it. 3. The first one, convex. That's just general convex. The second derivative is greater or equal to 0. Okay. Something can be general convex and not strictly convex and not strongly convex. Now, for the strictly convex, that should be greater than 0. But for the strongly convex, it has to be greater or equal to a particular number that I'm going to call mu. I'm going to show you as an example. Let me tell you this. Strongly convex, when function is strongly convex, it's automatically strictly convex. But when a function is strictly convex, it does not translate to strongly convex. A strongly convex is when you have a stronger restriction on the behavior of the curve. It has to be quadratic everywhere. Okay, now I'm going to show you some example. Okay, please pay attention. Okay, these are the conditions we're using. Go ahead. That's what? Oh, okay. You're going to see from the example now. Okay, go ahead. Exactly. What of w equal to 0? No, that's a constant. It's also convex. A constant function is a convex. You're going to see now. Let me show you this example. Now, if this is how to know, that's a good question. How am I going to know? I will differentiate twice. Now, take a look at this. Take a look at, these are the condition, right? Condition for convex, second derivative greater or equal to 0. For strictly convex, second derivative greater than 0. For strongly convex, second derivative greater or equal to a particular number. Now let's take a look at this. Please pay attention. Okay, this is where now let's take a look at this. If f of w equal to w, that's a straight line, right? When you do the first derivative of w, that will be 1. Second derivative 0. That satisfies convex because greater or equal to 0. Does that make sense? Now, if I investigate this, if I have an exponential function, when I differentiate several times, when I differentiate first time, it's still going to be exponential W. Second time, I'm still going to have exponential W. Okay? Exponential W is greater than 0 if W is positive. Yeah, that's an example of strictly convex. What about, I need you to pay attention now, because in the assignment and the test, I'm going to give you some functions, then I'm going to ask you to investigate for convexity. Now, take a look at the second one. Take a look at the third one. This guy. That's a quadratic function, right? And I told you the other time, quadratic function is quadratic everywhere, right? Let's see. It's a strong function. Let's see. Differentiate that. First time, that will be W. Second time, that will be 1. And 1 is greater than 0. That's a strongly convex. Now, do you now see how to investigate whether a function is a convex or strictly convex or strongly convex? Go ahead. Strictly convex is when it is greater than 0. When the second derivative is greater than 0, it must not include 0. That is strictly. Does that make sense? Yeah. Now, I'm going to move right now. Okay, I'm still going to make use of this material next time. I'm going to move right now. Okay, now let me now tell you this. What is the general formula for strong converse? What we want is strong converse. Okay, the general formula for strong converse is this. Take a look at this. If f of w, then it's a converse. Maybe it's strictly convex. How can we make it a strongly convex? Then I'm going to impose a constraint. That very constraint is mu over 2 norm squared, the square norm. That is the constraint that we introduce. So if this is convex, then it's going to be a strongly convex. The essence of strongly convex, we don't want it flat. Let me quickly show you something so that you can see what I'm talking about. Take a look at the two of them. Uh, Hello, can you see? Look at these two shapes. The first one is x raised to power 4. The second one is x raised to power 2. Then x raised to power 4 is strictly convex. Why is it strictly convex? Because it is flat at 0. Do you see flat? Do you see something flat at 0? But this guy is not flat. This is a strongly convex. We want our algorithm is going to behave well if you are working with a strongly convex function. Go ahead. Okay. Yeah, this is what happened. If I want to go by the picture, right? If I want to go by the picture, okay. Even if you do second derivative, right? And you plug in s equal to 0, what is going to happen? It's going to be 0. You understand what I mean? So what I'm trying to say is that when it is flat at some point, you can have a curve. Okay, the fact that it's a curve and it's above, and the line of segment is above it, it will be convexity. Okay, now when it is a curve, but you can have possibility of a flat, then it is not strong. But if you take a look at this guy, there is a curve, there is no flat anywhere. Therefore, your algorithm will not get stuck. Otherwise, when you make use of that, your algorithm is going to get stuck. So that is how it's going to. So if I want to look at the picture, okay, that is the explanation. Now I'm going to stop here. I'm going to use the same material when else we meet. Stay safe.